Okay, so for my experiment, I'm finding the tangential velocity of a pendulum at equilibrium, which you can find by setting potential energy at the very beginning to kinetic energy at equilibrium, because kinetic energy is at its max when the pendulum is at equilibrium. So you would set the mass of this times gravity times the height of the tennis ball, which you can find by first timing the period of the pendulum and using that to find the length of the string, and then you multiply the length of the string times theta, and my theta is 45 degrees, to find the distance, and you subtract distance from the length to find the height of the pendulum, and you set that equal to 1/2 of the mass times velocity squared. So that is how I'm going to find the tangential velocity of this. So first, put this at 45 degrees from the vertical, which would make it actually 135 degrees. And then you start the timer, and it gives you 2.66 seconds, which you then repeat this step 4 more times to get, and you add them together and divide them to get the average period, and then you find the length from that to find a more accurate string length than if you were just using one. So as I vaguely explained in the previous clip, my experiment is testing how the pendulum's length will affect its tangential velocity at equilibrium. The independent variable for this experiment is the pendulum's length, and the dependent variable is the tangential velocity, and also the pendulum's period is dependent, but that is just used for calculations. There were some control variables in this experiment, including the mass of the pendulum and the amplitude at which the pendulum is released. As the length of the pendulum increases, so does the tangential velocity at equilibrium. Because energy is conserved, we know that the potential energy at the beginning, since it's not moving, there's no kinetic energy, we can set that equal to the kinetic energy at equilibrium, since there's only kinetic energy at equilibrium. And so we know that the higher the pendulum is released at, the faster it'll be moving at equilibrium, since mass times gravity times height can be set equal to 1/2 of the mass of the pendulum times velocity squared. So with a longer pendulum, you get a higher height, resulting in a larger tangential velocity at equilibrium. And the procedure I used is I took a length of string and tied it around the circumference of a tennis ball, and I secured that with duct tape. And then I cut 8 unknown lengths of string, and I tied those around the string going around the tennis ball, and then I duct taped the string to the top of a door frame, and I pulled the string back until a protractor set on the top of the tennis ball was at 135 degrees or 45 degrees from the vertical, since you need theta from the vertical. So yeah, and then I released the pendulum and started the stopwatch at the exact same time, and then I stopped the stopwatch when the pendulum was back in my hand, and then I repeated that 5 times, and then I and then I added them up and divided the numbers and plugged them into the equations, which I'll explain in the next clip, and I repeated that whole procedure for every single length of string that I had.
So this is the work for the first length of string, and the first equation is used to find the average period. So it's all the periods that I timed divided by 5, because there were 5 trials, and that gives us an average period of 1 second. And then you plug that into the pendulum equation, which states that the period is equal to 2 pi times the square root of the length over gravity, So you set 1 equal to 2 pi over the square root of length divided by gravity, and that'll give you a length of 0.248 meters. And then to find the distance, you multiply that times the cosine of theta. In this case, theta is 45 degrees. So that'll give you a distance of 0.175 meters. And to find the height, you subtract the distance from the length, and that gives you a height of 0.073 meters. And since energy is conserved, you can set the height at the beginning of the pendulum period, which is completely potential energy, equal to the energy at the end or at the part where it's completely kinetic, which in this case is equal to equilibrium. So you set mass of the pendulum times gravity times height equal to 1/2 of the mass of the pendulum times velocity squared. And because mass is on both sides of the equation, you can cancel it out. And then you can manipulate the equation so you're solving for velocity, which would mean velocity is equal to the square root of 2 times gravity times the height, which would give you a velocity of 1.355 meters per second squared. The first 5 columns of this table are the periods that I found using a stopwatch, and then beside that we have the average periods, and then beside that we have the experimental length and the experimental distance, and then the experimental height, and then the experimental velocity, which the last 4 columns were all calculated using the formulas on the previous page. As you can see in the previous clip of the graph, the tangential velocity goes along the y-axis and the length goes across the x-axis. There is a slope of 1.545 meters per second per meter, since the tangential velocity is in meters per second squared and the length is in meters. There's a positive trend on the graph, which means that as the length is increasing, the tangential velocity of the pendulum is also increasing. Some potential sources of error is that the stopwatch could have not been started at exactly the same time as I released the pendulum. It also might not have stopped at the exact same time that the pendulum returned to the same spot. Another source of potential error is that when I released the pendulum, theta might not have been at exactly 135 degrees. A way to lessen the error is to have someone else starting the stopwatch, and some of the limitations are when measuring theta, it's hard to get exactly 135 degrees. Another limitation is that when measuring the actual length of the pendulum, which I did to find the actual numbers, which are in the next clip, I might have been off by a few millimeters because of the ruler I was limited to. Also, another limitation is how many decimal places over the stopwatch went to, and just the preciseness of the entire thing. My final conclusion is that it is true that the longer the pendulum gets, the faster the tangential velocity at equilibrium will be. This chart shows the actual values that I should have gotten during the experiment. I measured length of each string, and then I used that to find all the other values. And on the next slide, you'll see how I found period. To find the period, I plugged the length that I calculated into the formula. So I set the length that I calculated over gravity square rooted times 2 pi to find t. and to find all the other values, I plugged them into the equations shown at the beginning. This last page shows the equations for finding percent error. I found the average percent error, so I found the percent error for each individual length of string, and then I added that up and divided it by 8, and I got a percent error of 10.52. And since most of the other values were calculated using length, you can assume that the other percent errors are also around there. And the bottom one is for velocity, since you're using gravity to calculate it. It decreases the percent error, and that the final percent error for velocity is 5.3